students, in the previous lessons we have defined a linear transformation and studied its properties, and we proved that how a linear transformation exists from a vector space U into a vector space V. And also we have discussed about range and null space of linear transformation. Now here in this lesson we are going to discuss about matrix of a linear transformation. That means we want to establish a relation between function and a matrix, so that if you want to find rank of a linear transformation, then you can find rank of matrix. For that purpose, we want to construct a matrix for a given linear transformation. In fact, linear transformations and matrices have a very deep relationship. The study of linear transformations can be reduced to the study of matrices and vice versa. The matrix of a linear transformations provide a concrete way to represent and work with transformations. Once you have a matrix, you can perform various operations such as composition of transformations, you can find inverse, you can find rank by using matrix techniques. Suppose U and V are any two vector spaces over the field F, and n comma m be the dimensions of U and V respectively. What do you mean by this? The basis of U and V contains n and m elements. Then every linear transformation from U into V can fully described by means of a matrix of order m by n with elements from the field F. Before constructing a matrix, let us have definition of a linear transformation. Already we have given in the earlier lessons. If U and V are any two vector spaces, then a linear transformation from U into V is a function from t from U to V such that T of A alpha plus B beta is equal to A into T of alpha plus B into T of beta for every alpha comma beta belongs to U and A comma B in F. Now we will see linear transformations as vector spaces. Suppose if U and V are any two vector spaces over the same field F, and T1, T2 are the two linear transformations from U into V, the function, how you define T1 plus T2, T1 plus T2 at alpha equal to T1 alpha plus T2 alpha for every alpha belongs to U, which is a linear transformation. Easily you can prove that T1 plus T2 at alpha is equal T1 plus T2 at alpha is nothing but T1 of alpha plus T2 of alpha is a linear transformation from U into V by using the property T of A alpha plus B beta is equal to A into T of alpha plus B into T of beta. And how you define scalar multiplication? The above one, T1 plus T2 at alpha is T1 alpha plus T2 alpha is a vector addition. And how you define scalar multiplication? C of T at alpha is equal to C into T of alpha for every alpha belongs to U is a linear transformation from U into V. Now we will form the set of all linear transformations from U into V. We know that how many functions exists from a set A to B. Suppose if A has m elements, B has n elements, then there exists n to the power of m functions. So here also you will have so many linear transformations. You form a set and you denote it by L of UV. So L of UV, if you are writing, means the set of all linear transformations from U into V with respect to addition and scalar multiplication defined above is a vector space over the field F. Now we prove one theorem which is related, which we are going to use further to form matrix of a linear transformation. Suppose U is an n-dimensional vector space over the field F and V is an m-dimensional vector space over the field F. Then the vector space L of UV, just now I told L of UV is a vector space with respect to vector addition and scalar multiplication given by T1 plus T2 at alpha equal to T1 alpha plus T2 alpha and Ct at alpha equal to C into T of alpha. It is a vector space. So, now your L of UV is a finite dimensional vector space of dimension mn. That means, whenever U is a finite dimensional vector space with dimension m and V is with dimension n, then LUV, the set of all linear transformations, is of dimension m into n. For this, how to prove? Any time if you want to prove a set of vectors form a basis, if you want to find a dimension, you should get a basis. If you want a basis, you take some set of vectors and prove that they are linearly independent and they span L of UV. So, as a first step, suppose B is equal to alpha 1, alpha 2, etc. alpha n and B dash equal to beta 1, beta 2, etc. beta m be two ordered bases for U and V respectively. We know from the earlier lesson that there exists a linear transformation T from U to V such that T of alpha equal to beta, and also we know that it is a unique linear transformation. It is unique. So, there exists a linear transformation T11 from U into V such that T11 alpha 1 equal to beta 1, all other remaining you take it as 0. So, you define T11 from U into V such that T11 alpha 1 which is equal to beta 1, T12 alpha 2 equal to 0, T11 alpha n equal to 0, where beta 1 comma 0 0 these are all vectors in V. Actually, in fact, for each pair of vectors P and Q, there exists a unique linear transformation T P Q from U into V such that T P Q at alpha I is equal to delta I Q beta P. All of you know this delta I Q, what it is? It is called chronicle delta. Its value is either 1 or 0 based on the condition whether I is equal to Q or I not equal to Q. So, you have unique linear transformation. Actually, instead of defining T11, T22, T33 like that, I have defined TPQ alpha I, which is nothing but delta IQ beta P. So, here consider set of all these TPQ. How many there will be? Because your P can be any one from 1, 2, etc. m, and your Q, for P you have m choices, for Q you have n choices. So, for both P and Q you have mn choices. So, there are mn such TPQs. So, let B1 denote the set of all these mn linear transformations. Let B1 is the set of all TPQ such that T is a linear transformation. Now, we prove that B1, the set of all these linear transformation, mn linear transformation form a basis for L of UV. So, to form a basis, what you have to prove? You have to prove that it spans. Spans means every vector in L of UV is the linear combination of elements in its basis. So, you have T belongs to L of UV. Take T belongs to L of UV. Now, what do you mean by T of alpha 1? You have T of alpha 1 belongs to V, and this T of alpha 1 can be expressed as linear combination of elements of beta 1, beta 2, etc. beta m. Why? Because you have B alpha 1, alpha 2, etc. alpha n is the basis of u, and b dash beta 1, beta 2, etc. beta m. As T of alpha 1 belongs to V, this T of alpha 1 is the linear combination of elements of beta 1, beta 2, etc. beta m. That means you have T of alpha 1 is A11 beta 1 plus A21 beta 2, so on AM1 beta m, where all the coefficients A11, A21, AM1, these are all elements in the field. So, this in fine particular, if you take for I, this is T of alpha 1 for 1 less than or equal to I less than or equal to n. By generalizing, you get T of alpha I equal to A1i beta 1 plus A2i beta 2 plus and so on AMI beta m, or you have sigma p equal to 1 to m API beta I. Now, consider the linear combination of elements. How? S is equal to sigma p is equal to 1 to m, sigma q is equal to 1 to n APQ TPQ, which is a linear combination of elements of the basis B1, that means set of all TPQs. Now, since L of uv is a vector space, you have S also belongs to L of uv. Now, clearly S is a linear transformation because T is a linear combination, linear transformation T, because T is a linear transformation and S is the linear combination of linear transformations. So, S is a linear transformation. Now, we prove that S equal to T. If S equal to T, then we can say that S is equal to T equal to linear combination of T of alpha I. So, what is S of alpha I? Simplify. S of alpha I is sigma p equal to 1 to m and sigma q equal to 1 to n APQ TPQ at alpha I, or sigma p equal to 1 to m, sigma q equal to 1 to n APQ TPQ of alpha I. So, you simplify, this is nothing but sigma p equal to 1 to m and sigma q equal to 1 to n APQ delta IQ into beta p, or this is nothing but delta IQ is either 1 or 0. Therefore, you will get sigma p equal to 1 to m API beta p. It is nothing but your T of alpha I. Therefore, S of alpha I equal to T of alpha I for alpha I belongs to B1. Students, always I am advising you to take a pen and paper, do these steps. If I am explaining, while explaining you write, means it will be more clear for you. So, what do you mean? L of u v is linear, otherwise B is in linear span of B1. What is B1? Never forget, B1 contains all the linear transformations. Now, we prove that B1 is linearly independent, which is an easy task. We know that set of vectors alpha 1, alpha 2, etc. alpha n is linearly independent if every relation of the form A1 alpha 1 plus A2 alpha 2 plus and so on plus An alpha n equal to 0 vector implies A1 equal to 0, A2 equal to 0, etc. An equal to 0. So, like every time you take a relation of the form sigma p equal to 1 to m, sigma q equal to 1 to n, A p q T of p q is 0 vector. Okay. If you take, you simplify this, if you simplify, you will get, see, after simplification and using the properties of sigma, you will get B1i beta 1 plus B2i beta 2, etc. Bmi beta m is 0. So, that means you have B1i equal to 0, B2i equal to 0, etc. Bmi equal to 0 for 1 less than or equal to I less than or equal to n. That means whenever you are writing the linear combination of elements of TPQs, see here, when you have considered sigma p equal to 1 to m, sigma q equal to 1 to n APQ into TPQ 0, then all the coefficients of TPQs are 0. What do you mean? You have B1 is linearly independent. So, you have B1 is a linearly independent set of L of uv that spans L of uv. So, you have the dimension of L of uv is Mn, since B1 has Mn elements. So, this is for one observation to form matrix of a linear transformation. I hope everybody understood, because of many two sigmas, one for P and other for Q. Now, how you define matrix of a linear transformation? Why I told, because if you take a matrix of a linear transformation where U is m dimensional vector space and V is n dimensional vector space, then you will get a matrix of order m by n. Suppose B equal to alpha 1, alpha 2, etc., alpha n, and B dash equal to beta 1, beta 2, etc., beta m be ordered bases for U and V respectively. Now, see here, suppose if T is a linear transformation from U into V, each T alpha j can be expressed as a linear combination of beta 1, beta 2, etc., beta m. Just in the above theorem, how we proved T of alpha j is a 1 j beta 1 plus a 2 j beta 2, etc., a m j beta m. So, these scalars a 1 j, a 2 j, etc., a m j, these are all coordinates of T of alpha j in the ordered basis B dash. So, the m by n matrix whose jth column consists of these coordinates is called the matrix of a linear transformation, and the matrix of a linear transformation is denoted by T B B dash or simply by T. Okay. How you define this? It is T of alpha j, or the matrix of a linear transformation T is equal to a I j m by n, where T of alpha j is sigma I is equal to 1 to m a I j beta I for j equal to 1 to etc. n. Student, I hope the matrix of a linear transformation definition is clear to you. Let us have one working rule how to find when a given linear transformation is how to find the matrix of a linear transformation. At the same time, when a matrix is given, you have to find linear transformation also. So, first step 1, choose basis. That means to represent a linear transformation T from U to V with a matrix, first choose basis for the both domain and codomain. That means let alpha 1, alpha 2, etc., alpha n be a basis for U, and beta 1, beta 2, etc., beta m be a basis for V, and then apply linear transformation and write that vector as linear combination. See here, express each vector T of alpha I as a linear combination of the basis vectors of V. So, suppose T alpha I can be written as T alpha I equal to, otherwise T alpha j here, T alpha j is a 1 j beta 1 plus a 2 j beta 2 plus and so on a m j beta m is equal to sigma I equal to 1 to n a I j beta I. The collection or the coefficients a I j are the entries of the matrix representation of T. So, you construct the matrix T of alpha 1 coefficients, put in one column. Next linear transformation coefficients, put in second column, like that. The matrix A representing the linear transformation T with respect to the chosen basis is formed by placing the coefficients into columns. So, you will get a m by n matrix. Student, so keeping these points in view, in the first step what you have to do? Choose the basis, then apply linear transformation. That linear transformation, write it as linear combination of vectors in V, then those vectors in those coefficients in the form of columns, then you get a matrix of a linear transformation. Just I want to give an example here. Suppose you have a vector 1 comma minus 2 comma 5 as a linear combination of vectors 1 1 1, 1 comma 2 comma 3 and 2 comma minus 1 comma 1. How you write? What is a linear combination? You have alpha equal to a1 alpha 1 plus a2 alpha 2 plus a3 alpha 3. So, 1 comma minus 2 comma 5 can be written as a1 into 1 comma 1 comma 1 plus a2 into 1 comma 2 comma 3 plus a3 into 2 comma minus 1 comma 1. So, you will get 3 equations a1 plus a2 plus 2a3 equal to 1 and a1 plus 2a2 minus a3 equal to minus 2, a1 plus 3a2 plus a3 equal to 5. So, solve these equations and substitute like this. 1 minus 2 5 is minus 6 1 comma 1 comma 1 plus 3 into 1 comma 2 comma 3 plus 5 into 2 comma minus 1 comma 1. So, we take these coefficients minus 6, 3, 5 as a column vector in a matrix of the linear transformation. So, here let us do one example. Suppose define or you have a linear transformation T from R square to R cube defined as T of 1 comma 0 is 4 minus 6 1, T of 0 comma 1 is minus 2 7 0. Then find the matrix of T relative to usual basis. What are the usual basis? Means 1 0 0 1 is the usual basis for R square. For R cube 1 0 0 0 1 0 0 0 1, it is called usual standard basis. Actually, so now you see here x y is with you have 1 comma 0 and 0 comma 1 is basis for R2. So, you have x y can be written as x into 1 comma 0 plus y into 0 comma 1. Therefore, you have T of x y equal to x into T of 1 comma 0 plus y into T of 0 comma 1. So, apply linear transformation, you get x into 4 comma minus 6 comma 1 plus y into minus 2 comma 7 comma 0. So, form the equations 4x minus 2y minus 6x plus 7y comma x. Okay. Now, this 4 comma minus 6 comma 1 can be expressed as 4 into alpha 1, that is 1 comma 0 comma 0 plus minus 6 into 0 comma 1 comma 0 and plus 1 into 0 0 1. So, similarly T of 0 1 can be expressed as another column. The coefficients you see 4 minus 6 1, it is the first column. First vector coefficients are occupy first column. For the second vector you take second column. This is how you form a matrix of a linear transformation using usual basis or standard basis. Next one. This is look at this problem. You take pen and paper. Here linear transformation T is defined as T of x comma y comma z. Here it is T of alpha and T of alpha is alpha 1 comma alpha 2 comma alpha 3, like that. T of x y z is equal to T 2x plus y comma x minus 2y comma z. He is asking you to find matrix of this linear transformation relative to the basis. This is not usual basis and he gave another basis 1 comma 1 comma 1 and 1 comma 1 comma 0 and 1 comma 0 comma 0. Okay. So, your task is first task is find T of 1 1, T of 1 comma 1 comma 1 substituting for x, y, z and here you have 2 into 1 plus 1 comma 1 minus 2 into 1 comma 1. That means it is T of 1 1 1. How you get this value? By substituting for x, y, z. T of 1 comma 1 comma 1 is minus 3 comma minus 1 comma 1. Similarly, t of 1 comma 1 comma 0 is 3 comma minus 1 comma 0, and t of 1 comma 0 comma 0 is 2 comma 1 comma 0. After getting that, you write these vectors minus 3, minus 1, 1 as a linear combination of elements of these bases. Similarly, that you take it as first column of the matrix. Again you take 3 minus 1 comma 0 as a linear combination of these basis vectors form the second column, and again write my 2 comma 1 comma 0 as a linear combination of these basis vectors form the third column. So, how you form? I tell you one easy method. Suppose if you take x y z, x y z is a into 1 comma 1 comma 1 plus b into 1 comma 1 comma 0 plus c into 1 comma 0 comma 0, then you have a plus b plus c is x, a plus b is y, a equal to z. So, solving this, what you will get? A equal to z, b is y minus z, c is x minus y. Substitute these values, you will get t of 1 comma 1 comma 1 is, see here, 1 into 1 1 1 plus minus 2 into 1 comma 1 comma 0 plus 4 into 1 comma 0 comma 0. Similarly, t of 1 comma 1 comma 0, express it as a basis vectors. So, take these coefficients. See, what are the coefficients? 1, minus 2, 4, it is the first column. For the second vector, 0, minus 1, 4, second column, and third vector 0, 1, 1. So, that is the third column. So, in this way we will have matrix of a linear transformation, and after forming the matrix of a linear transformation, we will have similarity of linear operators. What do you mean by similarity? Suppose T1 comma T2 are two linear operators on a vector space V over the field F. What is a linear operator? It is a linear transformation from V into itself. Then T1 is said to be similar to T2, written as T1 tilde T2 if there is an invertible operator T3 on V such that T1 is equal to T3 inverse T2 T3. So, we can easily prove that similarity of linear operators is an equivalence relation. What do you mean by equivalence relation? Which is reflexive, symmetric and transitive. So, here what do you mean by, after defining similarity of linear operators, we say that two matrices A and B are similar if B is equal to C inverse AC. If B is similar to A, then we write B tilde A. So, we can prove that the relation of similarity is an equivalent relation, and one observation is, if two matrices are similar, then they have same determinant and they have same trace of the matrix. What do you mean by trace of matrix? Sum of diagonal entries, they will have same rank and same null space. So, students, in this lesson we have seen that the set of all linear transformations form a vector space with respect to addition of vectors given by T1 plus T2 at alpha equal to T1 alpha plus T2 alpha and C into T of alpha equal to Ct alpha, and we defined matrix of a vector space, and we have seen how to construct matrix for a given linear transformation. Thank you.